Many parts of the world, from Tokyo to Turkey, Chile to California, have experienced and are susceptible to earthquakes. These seismic events, which can cause millions of dollars in damages and also the significant loss of human life, largely in part to the collapsed structures. This raises the question, what if instead of collapsing or being damaged to the point where occupancy is no longer viable, structures were able to survive and actually right themselves close to their original position? This is the hope of research looking into the use of shape memory alloys, SMAs, as a type of reinforcement in concrete structures. SMAs, which are often have dentistry applications, as well as are used in those super elastic classes, can undergo deformations much larger than normal deformed steel and still come back to their original position. However, despite this amazing property, the fact that shape memory alloys are only able to be produced as smooth reinforcement bars raises the concerns that you would see a drop in bond strength. This means quite like an action star with sweaty hands trying to hold onto a person hanging off a cliff, or like a certain lion holding onto another lion, SMAs may reduce the strength of bond made with concrete due to its smooth surface, hence why traditional reinforcement actually has its distinctive ridges. Previous research has investigated the specific value of bond strength. However, there's lack of understanding on the global effect of this interaction on the flexural behavior of different structural elements and how incorporating new types of concrete may compensate for the loss in bond. As such, my research examines the effects emerging concretes have on the behavior of elements reinforced with shape memory alloys when compared to normal concrete. The current study consists of 8 beams split into 2 sets of 4 each, either comprised of normal concrete, which serves as a control, or of ultra high performance concrete, UHPC, an emerging type of concrete used in seismic resilient structures. Each beam in the set varies in the reinforcement used between conventional deformed or smooth reinforcement, as well as the arrangement with either hooked ends or straight exposed ends. All beams were tested in 4-point bending, which involves supporting the beams at 2 points 800 millimeters apart, while a load was applied at 2 points 100 millimeters from the center each. As load was applied by a universal testing machine, UTM, the midpoint deflection of the beam was measured using linear potentiometers, the UTM itself, and digital image correlation, DIC, with another set of linear potentiometers measuring the slip. DIC is a measurement methodology which uses a program that can track points of interest, in my case black speckles, across multiple images, converting the amount of pixels traveled into a displacement value. Based on this, we can take a look at the midpoint displacements outputted by linear potentiometers and the UTM. What we see is that the linear potentiometer has an overly steep initial response due to the fact that the instruments are not able to register the small displacements at the start of the test. On the other hand, the UTM data actually has an initial S-curve response due to the fact that different parts of the machine have to settle before you see movement in the beam itself. However, if we apply the results of the DIC to the UTM data, we see that the curve moves over to the origin and has a more reasonable initial response when compared to the linear potentiometer. This provides an objective method of correcting UTM data that still captures the overall behavior of the beams as evident with the peaks and drops all still being present. When comparing the flexural response of the beams using this data, we see that deformed steel beams tend to have smoother curves than those with smooth reinforcement bars, which have repetitive cycles of increasing load followed by sudden drops. These drops signify the slipping of reinforcement happening in the beams. The drops, as you can see, are more pronounced in the UHPC, as the steel fibers, which are used to make UHPC, can transfer the load, allowing for high strengths between increments of slipping. This can be further seen by examining the beam reinforced with smooth straight reinforcement, where increases in slip displacement can be seen to coincide with drops in load, with a proportional relationship between the size of a drop in load and the increase in slip displacement. Additionally, the use of UHPC is shown to improve the flexural behavior of beams reinforced with smooth bars, as the straight, smooth reinforced UHPC beam has a peak load of only 34.5%, lower than its straight counterpart, whereas when using normal concrete, the use of straight, smooth reinforcement has a peak load of 74.1% lower than its deformed counterpart. In summary, the use of DIC is shown to provide an objective method to correct data obtained from universal testing machine, and that the use of UHPC improves the flexural behavior of beams reinforced with smooth reinforcement when compared to normal concrete. These findings provide promise for the composite use of shape memory alloys, a smooth reinforcement, with emerging types of concrete such as UHPC. These findings will be further built upon in the future by testing an additional set of beams made using engineered cementitious composites. I would like to acknowledge the support of Dan Palermo as well as the Lassonde School of Engineering for their support in this project. Have a great day.